All right. So, hello guys. Here I am Tanjay Adakar and my friend Shaurya Srivastava, and we are here to explain an efficient local railway management system with using very appropriate data structures. Now, let's understand why this. Now, the main reason for me choosing this topic was because I myself travel via local railways, and what I have noticed personally is massive delays, which have caused me to being stranded at a particular railway station for maybe more than 1 hour or 2 hours at max. So this is here why I'm here to maybe given my inputs to tackle this situation. So why exactly this may happen is probably because of no efficient rescheduling. Well, I have noticed trains being kept at the trains being kept at the signals for a very long time and not being able to move forward. That is one of the causes. And then another one of the causes are the manual errors in rescheduling. Then the manual errors can also cause a very great damage. Like if suppose if a train is rescheduled and the platforms are changed, then that may cause into a massive rush and maybe even result into stampede, which may cause even greater loss of life as well as a physical damage to the train platforms itself. That's why we here are here to propose a robust train management system with very efficient rescheduling ways and a very way to undo the mistakes as well. Now, what are the key data structures used here? So here we have tried to implement four major data structures. That's the priority queue, hash map, linked list, and a stack. Now, priority queue. Here, the priority queue, what it does is like each delay is assigned a time-based function priority. So greater the delay, greater the priority will be. Now, hash map, since we all know, is a most efficient way to access the data faster. It's an O of one time complexity. So it's an immediate and fast access to the train data. And thus we can compute huge amount of trains, which are we're going to be passing to the station. Now the link list. The link list is the train's track-wise stops and where exactly we can understand where exactly the train is and maybe how longer it may take to reach a particular station. And stack, since we explained for maybe to undo some mistakes which may have happened due to human errors or maybe the system errors as well. Now let's look at the data structures in a little more depth. Now the first one is the priority queue. Here, the functionality, as mentioned earlier, is to store the time-based priority. The highest priority of the train is dispatched or rescheduled first. Now, the benefits of this is massive. That is the fair and efficient allocation of limited tracks, and it also prevents bottlenecks during huge amounts of delays. Now let's talk about the next data structure, that's the hash map. The purpose here is to fetch real-time train and station data. And since we all know a hash map is stored in a key and a value pair, so thus it's an immediate lookup time. So if we talk in terms of time complexity is bigger of one, so we can that's why we can compute huge amount of data in very small amount of time. Now, it also enables quick decision makings for rescheduling as well. And HashMap has a very cool feature that it can be seamlessly integrated with IoT sensors or maybe even GPS data as well. Now, let's talk about the another data structure, that's the linked list. Now, here's the purpose is to dynamically track the train schedule and the route. Now, the functionality is each node is a station in the train's journey, and this can allow insertion in middle, or maybe if the train has to skip a station, we can remove it very easily. Now, the benefits are obviously flexible and memory efficient as well, and it prevents a full structure change. Or we do not have to change the entire data structure, we can just manipulate it as we go. And to explain further, I have my friend Shaurya Srivastava here.
Hi. So I'll be going through last but definitely not least, the stack. So why do we use this? Its primary purpose is for to roll back incorrect or suboptimal scheduling decisions, and its functionality to push old schedule states into the stack before modification. And if we ever need to pop, then we can pop to revert if new scheduling causes conflicts. Now the benefits are obviously massive. Uh, first off, it adds safety and reliability to real-time automation. And last but not least, it prevents systemic errors due to faulty inputs. So, yeah. So the benefits of this product are obviously huge and have many real-life applications, such as real-time adaptability to dynamic conditions, reduced passenger chaos via automated recovery, transparent decision-making, and easier monitoring. And the list just keeps going on. You've got improved punctuality across the local network and data-driven insights for maintenance and forecasting. But how can we scale this, and what is its actual potential? Well, it's easily extendable to metro or national rail systems, which very much need the system in place. We can also integrate with AI modules for predictive scheduling. We can scale with distributed hash maps such as Redis or Cassandra. And we've got a cloud-ready architecture for multi-station deployment. And obviously, potential for smart city transport integration.
All right, so this is about our presentation. Now, Shaurya will continue on with the demo of the code as well.
Yep. Give me just a second. Tanuj, you can stop screen share. So here's the code functionality. Notice how we had to hard code some of the inbuilt functions since we weren't allowed to use some. And I'll just give you a quick demo of how our code works. So we start off with a CLI menu where you can schedule trains, list trains, report delays, and it's pretty much visible. But I will schedule this train to start with. We'll give it an ID, let's say 12. We've got 4 passengers. We'll give it 2 journey stops. Top one station can be, let's say, Mumbai. Arrival time is going to be at 5:30. We'll just do 5. Yeah, stop 2 is going to be at, let's say, Delhi. Okay. And that's going to be at 2300 hours. So we have added this train to the menu. So we can check it over here where we have seen ID 12, 4 passengers with a 0 minute delay. But what if there was a delay? Well, we can add it right here, ID number 12. We'll give it 30 minutes of delay. And that basically puts the priority queue system into place. So if we check out the priority queue, then we have given it an urgency of 6,000 that's mentioned over here. And as you can see, we can list out all the trains. Now it has been given a 30-minute delay. We can also undo last action, edit the journey, as you can see here. That's show it gives you the details over here. And the last few functions are things that we plan to put in progress in the production stage and have not been completely implemented yet. So that's basically it from the code perspective. Um, we'll be moving on to the questions next.
So hello Shaurya, hello Tanuj. So starting off with the presentation mentions manual errors as a key problem. Which specific data structure from your solution is designed to handle this? And what is the exact process to use it, to it uses to undo a mistake?
All right, so to undo a mistake, that's exactly where stack comes into the picture. Now, stack, the main use of it is to pop off something which you don't require. Now, here exactly is where a stack is used. Now, before a system commits probably a new scheduling decision, so it is first pushed onto the old stack where it can be customized. And suppose if there is a manual error or maybe a system generated error, probably the number of passengers is wrong, the delay is wrong, we can just pop it out, edit it, some of it, and then push it back. So this is a very key concept which can be used. So I think with this into the picture, I think train scheduling and the manual errors can be minimized to a great extent.
Okay, all right.
In your code, you have used the train hash table class, which uses linear probing to handle collisions. So, what would happen if you try to store more than 10 trains? And why might this be problematic?
So that's a great question, Sushant. But here's how we dealt with it. If you try to store more than 10 trains, then right now the hash table will fail because we have a fixed size of 10 slots. But if we wanted to improve this, we could implement dynamic resizing, where we rehash when load factor exceeds zero point 0.7, as we've mentioned in the code. Or we could use a larger initial size to switch to chaining, where we use linked list at each slot instead of just linear probing.
Continue with your question about hash maps and hash tables. How do the hash map and the priority queue work together to handle a train that is suddenly delayed by an unexpected event?
All right, so there's a two-step method. So the first is the date update or the data update. So here the hash map with its O of one lookup, that's the instant lookup. So when a train is delayed, its status, like probably the delay info or its current location, is updated in a hash map and using the train ID as a key. And the urgency resort is done by priority queue. The priority queue then reads the new information into the hash map. It uses that data along with the other factors, that probably the passengers, how much time the train is delayed, to calculate the train's urgency. And then the queue is automatically resorted. So a hash map, the use of hash map here is to provide the new data, and the priority queue instantly uses that data to reprioritize the train as required.
In the report delay feature, the urgency is calculated by a certain formula. So can you explain why this formula might be counterintuitive?
So I think you got it wrong. The formula is actually inverted. It treats lower values as higher priority using a min heap, right? And trains with more passengers get lower urgency numbers because of the division, which is our formula 1000 divided by passengers plus one. So I'll give you a short example. Let's say that there is 100 passengers, and then we get the urgency of 10 per minute of delay. Then 10 passengers means 90 per minute. That means trains with more passengers are rescheduled first, which makes sense, obviously, because it impacts more people. But the variable name urgency is a little bit misleading since the smaller numbers are actually higher priority in this heap.
Right. So you suggest using a linked list for journey tracking. Why is this structure more flexible and more memory efficient for this task than using a simple array?
So, I mean, it's a good question. So, see, an array is a static memory allocation. So, you're probably just uh, reserving a very limited space for these trains, and you may underutilize it, or maybe there might be an overflow. To fix that, the linked list comes into the picture. So, what exactly a linked list does, since it's dynamic, so we are using appropriate amount of RAM onto our servers that will help us into making it more efficient, memory efficient, as well as process efficient itself. And linked list itself is far more flexible. As for each node, which is a station, it can point to the next station destination, as well as store a particular delay by which it is going to arrive at the station. And probably, let's say a train is going to skip a station, so we can just skip the another next pointer to the next. So indirectly, that particular station is skipped, and to maybe insert a new station. Probably the train is going to stop another station. We can just create a new node and adjust the pointers as we require. So this prevents the system from having a full rebuild the entire structure. So if you use an array, you'll have to discard the previous array if you're going to insert or delete something and create a new array to implement this entire thing. But in linked list, that's not the case. You can easily implement it with minimal hassle.
All right.
The system seems to be designed for a local network. So according to you, what are the key ways in which the system architecture could be scaled up to handle an entire national rail system?
Yeah, actually, you're correct. Right now, we have designed this for a local network, but when we decide to go into production, then I think as we mentioned, we can use distributed data. So right now, instead of using one giant hash map, the system can use distributed hash maps like Redis or Cassandra, like we have, right? So this spreads the massive amount of train and station data across so many servers, right? So no single machine is at a bottleneck. And we also have cloud architecture, right? So we've made it cloud ready. That means as soon as we deploy it, right, we can deploy it to a scalable cloud infrastructure, which has horizontal and vertical scaling, where you pay as you go. So if the network expands, you can just add more computing resources in the cloud to manage the increased load from multiple stations and reach it simultaneously.
Yeah, I'm much satisfied with your responses. But picking out here from the questions from the thought of PPT, slide 2 identifies no efficient reschedule and massive rust as a major problems. how does a priority queue specifically help reduce both of these issues?
Alright, so priority queue here creates an automated and a fair system to manage such a huge chaos. Now it solves no efficient rescheduling. Well, instead of a slow and a manual process, the queue automatically sorts itself with the delayed trains by urgency. So let's say when a track is free and the system initially dispatches a high priority train, making the entire rescheduling process a very highly efficient. And obviously, it again solves massive rush because the system is fair and prioritizes train logically. So it kind of prevents bottlenecks as well. It avoids situation where one minor delay can cascade in and causes all the trains to probably delay by even more time. Thus, by allocating all the trains efficiently, it smooths out the flow of train, and as a result, it kind of also inherently reduces the passengers' chaos as well, which may be caused due to abrupt changes of the train's timings.
Right then, that was our question here for you guys. And would you like to conclude your work?
Yes, so that was it. I mean, thank you very much for giving your time to us.
Thank you.
Yes. Okay.
Disaster relief resource management system. Our aim is to efficiently manage emergency relief operations using data structures like graph and priority queues. In real life situations such as flood or accidents, multiple locations might need help at the same time. So our system helps decide which area to attend first and what's the shortest route to reach them. So these are the contents. According to our problem statement, these are the three factors which we will work on. So, what are the impact of natural disasters on relief operations? They disrupt infrastructure and communication and also deplete resources, which complicate relief efforts and delivers aid delivery. This point highlights the critical need for our management system. Also, when a disaster is occurred, multiple locations might need help at the same time. So, our system helps to ensure which urgent request might get help at the first. So there's also need for prioritization and efficient routing. So these are the objectives of the resource management system. Our system ensures that resources are prioritized according to their urgency. For example, medical emergencies come before food or shelter requests. This allows us to allocate resources swiftly and minimize risk and address critical needs first. So we also have optimizing delivery routes for speed. Through route optimization, the system finds the fastest and the most cost-effective delivery path. This not only reduces fuel consumption, but also saves time, ensures that essential supplies reach affected areas without delay, enhancing overall disaster response efficiency. By reducing communication gaps and delayed efficiency, the system promotes better coordination among teams. This leads to optimized resource use and accelerated relief efforts, improving the overall effectiveness of disaster response. So, what all concepts of data structures have we implemented? So, for the first, we have implemented graph in representing affected regions. So, let's say a certain area has gone through a landslide. So, we have decided to represent nodes as location and edges as roads. And also, we have decided to use traversal methods like BFS and GFS, which help in finding the shortest path. So, what is the importance of graph in route finding? Graph efficiently model affected regions and routes, enabling dynamic route finding by representing locations and nodes and partner edges, which is very crucial for optimizing disaster relief logistics and response time. Another concept of data structures we have implemented is priority queue. So it defines priority levels for different requests. It categorizes requests based on urgency and impact, enabling to efficiently allocate resources and not waste it. Handling critical medical requests first. So it manages disaster relief requests by ensuring medical cases receive immediate attention Other than that, we have queue management for efficient scheduling. It organizes tasks in order of urgency and importance, ensuring that time-sensitive operations are executed promptly. We have also used shortest path calculation. We have used Dijkstra's algorithm, which helps in finding the shortest path between nodes and graph. Let's say you have a weighted graph, and we have decided to use the edges as roads, and so the weight which will be represented on the edge will be used to represent the traffic efficiency. So let's say you have a traffic of level 43 on one edge and traffic of level 5 on other edge. So this algorithm will first traverse to all the edges and take the shortest crucial path to reach the destination. These are combining priority queue and graph for decision making. It improves workflow and representing locations is made easier. This integration enables efficient route selection, optimizing resource development during disaster relief operations. And it efficiently prioritizes and routes critical requests, ensuring timely resource allocation and improved disaster response outcomes. It also integrates priority queues with graph algorithms to enable efficient real-time resource allocation by dynamically prioritizing relief tasks based on urgency and network connectivity. For further emphasis on benefits and potential enhancement, I would like to hand it over to Avnish.
Hello, everyone. Myself, Avnish Sawant, and now we are talking with the further announcement of our projects. So, improvement in disaster response efficiency. So, on the left side, we talk about speed. Faster resource delivery means that relief materials like food, medical aid, or rescue teams reach affected areas quickly. This is not only reduces response time but also improves coordination and minimizes delays. Ultimately, it helps save more lives and resources because the help arrives when it most needed. Effective management of multiple concurrent requests. On the right side, the shift of efficiency, how to manage multiple emergencies happening at the same time by prioritizing and allocating resources properly. We reduce confusion and overlap. It ensures that no area is left waiting too long. And that also response team are working together effectively. And now I would like to, Sushant, can you
Yeah,
move on to the next slide? Yeah. I also like to talk about the feature enhancement and scalability of our project. That is integrated real-time data with sensors like it enhances disaster response accurately, more accuracy, more fastly. It reduces, minimize the delays, and then expanding different types of disasters that we are not included right now at the moment in our projects. Then we also incorporating machine learning models to predict analysis. And now I would like to show you the demonstration of our code. And Sushant, can you stop the
yeah.
screen sharing? So yes, this is the code we have written for the whole disaster relief management system. And I would like to quick run through the main system we have enabled here. And yeah, I hope it's visible. Yeah. So the main function I basically simulated a small disaster management system that decides which location to help first and how to reach it using the shortest path. I started by creating an object called system that stands disaster manager. And here I passed two parameters, that is 5 locations and 0 at the headquarters. So uh, the the locations are not to be numbered. That's why we have given it in the alphabetical order. HQ stands 0 and then A, B, C, D. And then all these locations stand for village A, B, C, and D. After I connected this location using the function ADRD, which stands for adding the roads or the adding the paths to the system or to the area affected. Then uh, for example, HQ to village A had a distance of 4 units, and HQ to village B had a distance of 2 units, and so on. Basically, this forms the maps of networks of routes between villages. And I simulate the disaster request, each request has a location and an urgency level. Lower urgency number means it's more critical. So village which urgency 1 gets help before urgency 3. So I add three requests village C with urgency 1 with that is the most urgent request, and village D with urgency 2 and village A with urgency 3. Finally, I call process request function which uses Diksha algorithm, and after that I would like to quick run through and show you the output of our program. Yeah, so here we can see handling request at location 3, that is village C with urgency 1, and the total distance covered is 9 units. And the same village with the HQ to village D, it's 11 units. And hence, so on and so forth. This can be hard coded, and also from we can take an input from the users. And now I like to move on to the questionnaire section. Before that, we would like to present PPT again. Yeah, guys.
Well, during the presentations, you mentioned you're using graph structure for route management. Could you explain how exactly graph was represented in your program, and why did you prefer that representation over others?
Yeah, sure. So in our system, I represented the graph using adjacency matrix, which is basically two-dimensional array where each cell stores the distance between two locations. I prefer this over an adjacency list because we are a tree, you said, tree data structure. We had a small and fixed number of locations. So space wasn't big issue. Also, it makes checking the connection between two places in constant time or big O of one, which was useful for finding routes quickly in emergencies. So yeah.
Okay. Another question. So you talked about handling multiple disaster requests using a priority queue, right? So how does that actually help in optimizing which request is handled first?
Yeah, so the priority queue lets me automatically sort requests based on urgency. So each request has an urgency level, and the one with the smallest urgency value, which is the most critical, is processed first. This also ensures rescue operations are handled in a realistically order, just like an actual emergency system.
I noticed you used Dijkstra's algorithm for finding the shortest path. Could you explain in simple terms like how exactly your algorithm decides which path is the best?
Yeah, sure. So Risha starts from a source like the HQ in our case and keeps checking all possible paths to reach the other location. It always picks the currently known shortest distance and keep updating as it finds the shorter routes. It uses the concept of relaxation if a new path offers a shorter distance to a node. It updates it and finally it builds the shortest route to the destination step by step and until it reaches the target location.
I had a look at your code and it looks like you used multiple classes. Could you tell me how your object-oriented programming concepts actually made your program easier to design or manage?
Yeah, so we use three main classes, which is graph, RxT for request, and Dishman for disaster management. Also, the concept we have used are encapsulation. So each class handles its own data, like adjacency matrix in graph. The second one is abstraction. So the user doesn't need to know how the path is calculated internally. We are just denoting it SHR short path. And the last one we have used is modularity. It's easy to update or debug parts separately. So the structure has made a program clean and reusable.
I have another question. Suppose if I wanted to see not just the shortest distance, but also how many roads or the edges the person or the system has to traverse throughout the travel. So how could you modify your program to accommodate that?
Okay, very well question to our programming knowledge here. So that's a small addition in the shortcut function. After printing the path, I can count how many edges were used by simply checking the size of the path vector. In addition to finding the shortest path between two locations, how can we determine the number of roads or edges that you have mentioned that were traversed along the path? To address this, we can enhance the short path function by analyzing the path vector after the short path is computed. Since the path vector stores the sequence of nodes visited, the number of edges is simply one less than the number of nodes in the path. Therefore, by printing path.size from function, that is inbuilt function, we can display the total number of edges traversed during the short path computation.
Okay, so far so good. But let's say suppose one village got disconnected from all the others due to like a road blockage or something. So is there a way to check how which locations have like no connections at all or something?
That's an excellent question. Yes, I have added a helper function to identify such isolated nodes. So suppose a village becomes completely disconnected from all the others due to a road blockage. Is there a way to detect which location have no connections at all? Yes. This can be achieved by adding a helper function that scans the adjacency matrix for isolated nodes. For each village, we check whether it has any active connections to other villages. If none are found, we declare the village as isolated. The function then prints out the names of all such locations or none if every village is connected to at least one other.
All right. So one last question from my side is, let's say, probably for the worst case scenario, may and God may forbid, what if two villages at the same time have the same urgency level, and let's say it's the worst urgency, probably the medical urgency. So how exactly would that scenario be handled?
Yeah, excellent question again. That's a very real-time data we are providing nowadays. Like in that case, I would prioritize that one that's closer to the headquarters, the HQ. To simulate that, I slightly modify the comparator using the priority queue. In our disaster response system, how should we handle multiple requests that have the same urgency level? One practical approach is to prioritize a request that is geographically closer to the HQ. This can be implemented by customizing the comparator using the priority queue. Specifically, we can define a comparator that compares requests based on their locations, time, or distance, ensuring that requests from nearer locations are handled first when urgency levels are equal. The mirror real worlds reflect relief operations where proximity often influences response speed.
Okay,
So,
I think that concludes the questions from our side. Yeah, you guys can wrap up.
yeah, so thank you guys.
Thank you, guys.
This